Introduction to light. Light is an electromagnetic wave. It is a transverse wave. Here are your priming questions. We're going to move on. Before we talk about what light actually is to our current understanding, I want to quickly talk about some of the early concepts. There are a lot of different early concepts, but here's just a few that are important. The Greeks, they thought that particles caused sensations of visions. This is actually pretty close to the truth. From there, we have Socrates, Plato, and Euclid, and they thought that the vision came from the eyes and to the objects. And so some of these early philosophers and Greeks, they actually thought that there would be things that came out of your eyes, and only once your eyes settled on something could you see it. And this actually makes sense from that perspective, because sometimes you don't see something until your eyes actually look at it. And so this was their concept of vision and of light. From there, we have some early scientists, and at that point we knew that light was a wave, except the scientists thought that light was only a wave. And they did a lot of experiments to show that light could act as a wave. And then Einstein comes along, and Einstein discovered the photoelectric effect. And the only way that you would be able to explain the photoelectric effect would be with a particle nature of light, which flew against the idea that light was a wave. And so this changed our understanding of light into what we know about it today. So the photoelectric effect, this means that there is a wave that hits a material. It interacts with that material and causes an electron, or causes a particle, to be removed. This showed the particle nature of light, which was different than if light was purely a wave. And so there's a good video that I found that helps to show this. And so this shows the wave-particle duality. And this is if light was only a particle. This is what's called a double-slit experiment. This would be the expected result. Now, if it were a wave, then you would actually see what's called an interference pattern. And you can see as the wave goes through the two slits, you see this interference pattern of the two waves. From there, if it were a quantum object, which is as it is, the wave-particle duality, you can see that it acts differently as well. And you'll see the interference pattern there still. An interesting part of the experiment, though, is when you add an observer, it changes the results of the experiment. And this we can talk a bit more in class, but just simply adding an observer alters the experiment that the scientists did. And so light travels as a wave, but interacts with matter as a stream of particles. And this is part of the quantum aspect of light. And so we have this wave-particle duality, and part of it really is that light has its own nature, and the way we've come to describe it the best we can is through understanding it as a wave as well as a particle. It is both at the same time. Now, the speed of light. If you remember from the last unit, it's 3 × 10⁸ meters per second. The way we measured this was through a number of different very interesting experiments that we were able to do. We were able to use Jupiter's moon to show that light had a finite speed based off of where Jupiter was relative to the Earth and the Sun. And so at different points in time, we would be at different distances. And when we would see the moon come around Jupiter, we would have a different amount of time. And so we were able to show that light had a finite speed, which up until then, it pretty much seems that light is an infinite speed. And so everything happens simultaneously. Also, Michelson did a really interesting experiment with a rotating mirror around on a mountain, and basically shined a light. It went to a mountain across, reflected back, and based off of the rotation of the mirror, he was able to measure the speed of light. And so, as a quick exercise, I also want you to figure out how far light can travel in 1 year. This is what we call a light year. So I want you to figure out that distance in meters. And you'll check your answers with the people around you in class. So some fun facts. These are I won't hold you responsible for, but they're very interesting. Light from the sun takes 8 minutes to reach us. So if something were to happen to the sun right now, we would have no idea for 8 minutes, and then it would go black. Also, gravity operates at the speed of light as well. And so if something were to happen to the sun, we would not feel it on the Earth until 8 minutes, when the Earth would go dark. The nearest star to us is Alpha Centauri. It's about 4 light years away. So it takes light 4 years to reach us. So the light that we see today was actually produced 4 years ago. Our galaxy is roughly 100,000 light years in diameter, which means for light to go from one end to the other end takes 100,000 years. And some galaxies are 10 billion light years away. So if we see them, the light that we see was produced 10 billion light years ago. 10 billion years ago. Our universe is, I think, about 12.8 billion light years. 12.8 billion years, according to most recent calculations. Materials. When light shines on an object, the electrons in the matter are forced into vibrations. Now, depending on what those electrons do to that energy, determines if the material is transparent, opaque, or reflective. When we talk about light in this manner, the unit of light that we are using is what we call the photon. And it's the interaction of this photon with this electron. So right now we're referring more to the particle nature of light because it's interacting with matter. And from here, for transparent, when this photon hits the atom, it's absorbed by the electrons and causes those electrons to vibrate. From there, the electron actually holds onto the proton for a short amount of time before it passes on, and it repeats this until the photon has passed through the material, whatever it is that is transparent. Now, this causes a delay for the light to go through that medium, which means that as light goes through a medium, the speed is less than in a pure vacuum. This actually causes the light to change its direction with what we call bending of the light through a medium as it refracts as it goes through the medium. Hopefully you remember refraction. Now, opaque or opacity. This is when the material does not allow light to be transmitted. So what happens is the same steps before, the photon hits the electron, but now when the electron vibrates, those molecules, rather than allowing that photon to pass through, it turns that vibration just into kinetic energy. It heats up the material. Now, this property depends on many different things about the material, the frequency of the radiation, and when we say light is simply part of the electromagnetic spectrum. We use all different types of radiation, and what's interesting about this is that, just as a statement on the bottom, there are certain materials that are transparent at certain frequencies and opaque at other frequencies and reflective at other frequencies. So if you think of the piece of glass that is in your window in your house, it most likely has multiple layers of films that have been attached to the glass. Now, it's hard for you to see it other than in a reflection, and you'll see it as a purplish or blue or maybe even a green color. Now, what these films do is they're designed to allow visible light through, so it is transparent to visible light, but it is either semi-opaque or as opaque as possible to these other ranges. So in the infrared and ultraviolet range, it is opaque to those frequencies. And as in the same example as before with X-rays, if you think of the way an X-ray works, with X-rays, your flesh, your tissue, is transparent to the X-rays. Your bones are opaque to it, and that's how the X-ray actually works. Now, for metals, the electrons are not bound to the atoms. So if you think back to chemistry, this is the electron C model. Now, so when light causes the electrons to vibrate, the energy is actually re-emitted as visible light seen as a reflection. So when you highly polish a piece of metal, or when you have that coating of metal on a mirror, that's what's happening. The photon hits the electron then re-emits that photon, which we perceive as a reflection. And here are your priming questions again.